Okay. 2.2.0 using geometry to make a bend. Calculating bends 2.2.1. A right triangle like the one shown in figure 16 is defined as any triangle with a 90-degree angle. Important concepts related to the components of a right triangle can help you create offset bends. Listed below are descriptions of a right triangle's primary components. So here's figure 16, right triangle and offset bends, and it's highlighted. So here's our right triangle. Here's the base of the triangle and the height of the triangle and the hypotenuse. I don't know why they would have drawn this up in the air. I never do that. I always leave the base on the ground, and then the height is the height of the offset. This triangle should have been drawn underneath our offset with the base and the height, because the height of the obstruction is what we're interested in. All right. Highlight. The hypotenuse is the side directly opposite the 90-degree angle. The base is the side on which the triangle sits, and the height is the vertical side. The offset forms the hypotenuse of a right triangle. So this goes on to talk about a circle. A circle is a closed curved line whose points are all the same distance from its center, the focus. There's the focal point of the circle. These circles all have the same focal point. The radii are different lengths, but the focal point is the same. These are called concentric. And when you get real good at pipe bending, you can bend your conduits to be concentric 90s, and it looks really nice. So here is the rate. Well, all right, I'm going to argue with the book. The radius of our bend actually goes to the center line of the conduit. We always measure our radius to the center line of the conduit. So if they said an 18-inch radius, it would be going from the center of the conduit. No, center of the conduit here. Oh, maybe I can zoom in now. There we go. That didn't help. All right. Anyway, it's the center line of the conduit. What does this tell me here? All right. The length from one edge of the circle to the other edge through the center point is called the diameter. The diameter is always twice the length of the radius. Radius is one of these lines from the center to the edge of the circle. All the way through the circle is the diameter. The circumference is the distance around the circle, and you can divide the circle into 4 equal quadrants. Each quadrant accounts for 90 degrees, making a total of 360. So there's r squared times pi. Well, you can say half pi times the radius, or I'm sorry, it's 2 pi r is the circumference. 2 times pi times the radius. So pi times the radius would give us 180 degrees, and a half of pi times the radius would give us 90 degrees. That half pi is 1.57. That's what we use to find developed length, is 1.57 times the radius of the bend. The distance from the center of the point of the edge of the circle is called the radius. Concentric circles are circles that have a common center but different radii. And you can apply the concept of concentric circles to concentric bends in conduit. The angle of each bend is 90 degrees. Such bends have the same center focal point, but the radius of each is different. All right. So it goes on to say a circle can be divided into 4 equal quadrants. Each quadrant accounts for 90 degrees, making a total of 360 degrees. When you make a 90-degree bend, you use a quarter of a circle, or 1 quadrant, a bend that changes direction of the conduit by 90 degrees. Concentric circles are circles that have a common center but different radii. When bending conduit, the concept of concentric circles can be applied when creating concentric bends, making 90-degree bends in 2 or more parallel runs of conduit and increasing the radius of each conduit from the inside of the run toward the outside. So to calculate the circumference of a circle, use the following formula. It's 2 times pi times the radius, or pi times the diameter. To calculate the arc of a quadrant, use 1/4 of 2 pi times the radius. So you're going to use 2 pi, we'll divide it in 2 and get pi times the radius, and we'll divide pi by 2 again, and we'll get half of pi, 1.57. Remember, pi is 3.14, so half of that is 1.57. For this formula, a quadrant's arc equals 1/4 of the circle's circumference, or 1.57 times the radius. A bending radius table is included in Appendix 23B. So let's see what they have to say here. 2.2.2. Making a 90-degree bend. A 90-degree stub bend is probably the most basic bend of all. You'll use the stub bend most of the time, regardless of what type of conduit you install. Let me see here. Here's a highlight. Before you begin making the bend, you need to know 2 measurements: the desired rise or stub up, and the take up, the distance of the bender. Desired rise, the height, is the height of the stub up. The take up is the amount of the conduit the bender will use to form the bend. So I have to go back to my magic board. Okay, so let me see how well I can do with this. If I have, okay, this bender has different marks on it. First mark we need to discuss is this arrow. The arrow is for making stub ups, 90-degree bends. And usually for a 1/2 inch EMT bender, the take up will be 5 inches. What take up means is that when you coin this bend, when you've bent a 90-degree bend, and this bender is sitting in this orientation, this arrow is going to be 5 inches off the ground. So if you want an 8-inch 90, you're going to subtract the take up of the bender. You'll subtract that 5 inches, and you'll mark the pipe at 3 inches. And then when you put your bender on the pipe, you're going to put it lined up with that arrow on that mark. And then you can bend this up. And when that happens, when you bend this up, you'll see, let me scroll down here, you'll end up with a 90 that is 8 inches, will be 5 inches to the arrow, plus that 3 inches. I know this isn't really, it's not to scale, but we'll end up with an 8-inch 90 if that's what we wanted. If we want a 10-inch 90, subtract 5, mark it at 5 inches. If you want a 12-inch 90, subtract 5, mark it at 7. What I like to do is to take, and I'm going to make just a really poor drawing here of a tape measure. Here's my tape measure. What I like to do is take the tape and extend it 5 inches past the tape, the end of the conduit. So if this is the 5-inch mark on my tape measure, now this would be 8, this would be 10, this would be 12. You can mark on the pipe whatever the mark is, 8 inches mark 8, 10 inches mark 10, 12 inches mark 12. You've already taken the deduct, you've subtracted it by hanging it over the end of the conduit. So whatever the take up of the bender is, you hang that tape over the end of the pipe at that mark. And then you can just mark exactly what the measurement is for the 90. Let the tape do the subtraction for you. That way you're less liable to make a mistake, a math error. All right? We'll go back to the book. I think there's another mark. There are a couple different marks we'll have to talk about. There's also a rim notch, and that rim notch is the center of a 45-degree bend. So we use that center of a 45. We'll also talk about the star on the bender right there. That's used to make back bends, back-to-back 90s. Okay. So let's go back to the book and continue reading, see what they've got here. All right. It says, now that you've determined the take-up, you're ready to make your 90-degree bend. Use the steps below to make the bend. Subtract the take-up from the stub height. Again, our stub height was 8 inches. We subtracted the 5-inch take-up. We marked the pipe at 3 inches. Mark that distance on the conduit all the way around the conduit at the distance from the end. The mark will indicate the point at which you will begin to bend the conduit. Line up the starting point on the conduit with the starting point on the bender. Most benders have a mark, such as an arrow. Here's their arrow. They'll line that up with the start mark. To indicate this point. Figure 19 shows the take-up required to achieve an 18-inch stub up on a piece of a half-inch EMT. So an 18-inch, if we subtracted 5, we'd be marking it at 13 inches. There you go. So you want an 18-inch stub up. We're going to deduct this 5 inches from the arrow. Again, when we rotate this 90 degrees, that arrow is going to be 5 inches off the ground. That's where that take-up comes from. It's not the distance traveled, because that would be 1.57 times the radius. So it would be closer to 7.5 inches. But this arrow will be 5 inches off the ground. Plus this 13 will give us our 18 inches. There's the height of the stub up, 18 inches. Matching bends and parallel runs. So suppose you're running a 1-inch rigid metal conduit along with a 2-inch rigid metal conduit in a rack, and you come to a 90-degree bend. If you use a 1-inch shoe, the radius would not match that of the 2-inch conduit bend. To match the 2-inch 90-degree bend, take the 1-inch conduit and put it in the 2-inch shoe of the bender. Then bend as usual. This 1-inch 90-degree bend will now have the same radius as the 2-inch 90-degree bend. This trick will only work on rigid metal conduit. If done with EMT, it will flatten the pipe. Step 4, when you have lined up the bender, use 1 foot to hold the conduit steady. Keep your heel on the floor for balance. Apply pressure to the bender foot pedal with your other foot. Make sure you hold the bender handle straight and as far up as possible to get maximum leverage. Bend the conduit in one smooth motion, pulling as steadily as possible. Avoid overstretching. Also, when pulling, be careful not to place your face or head where it may get hit by the bender. So, when bending conduit, using the take-up method, always place the bender on the conduit and make the bend facing the hook of the conduit from which the measurement was taken. So, after finishing the bend, check to make sure you have the correct angle and measurement. Use the following steps to check the 90. With the back of the bend on the floor, measure up to the end of the conduit, stub up to make sure it's the right length. Check the 90-degree angle of the bend with a square or the angle formed by the floor and a wall. A torpedo level may also be used. I should say that this metal conduit has something called spring back. So when we coin our bend, we're not going to bend up 90 degrees. If we do and we let go, we'll have about an 87-degree bend. When we bend, we're actually going to bend over to about 93 degrees. And then when we let go of the pipe, it will relax back to a 90-degree bend. So you need a little bit more for spring back. I just wanted to point that out because I didn't say that. 2.2.3, determining the gain. To properly bend conduit, you need to know how to determine the gain, the distance saved by the arc of a 90-degree bend due to conduit being bent in a radius and not at right angles. The gain is the distance saved by the arc of a 90-degree bend. So here's distance A, here's distance B. The pipe is shorter than those two distances added together. It's shorter because it's taking a shortcut. It's taking a curve, which is 0.43 times the radius shorter than the measurement given here. So if you knew what the radius of the bend was, then you could multiply by 0.43 and find out what the gain is. But they're saying for half-inch conduit, it's a 4-inch radius and 2 and 5/8 inches of gain. 3/4 inch conduit has a 5-inch radius and 3 1/4 inches of gain. 1 inch has a 6-inch radius and 4 inches of gain. An 1.25 has 8 inches and 5 5/8 inches of gain. All right. Let's see. To find the gain, add the length of stub up A to the remaining measured length of conduit after you've made the bend. So what they're saying is if you have a piece of conduit, you can measure that conduit. And then after you've measured the length of it, let's say the conduit was exactly 36 inches. It's 3 feet long. You have a piece of conduit that's three feet long. And it's a scrap piece, so it doesn't matter. You can put a 90-degree bend on that 36-inch piece. And then we'll add the two legs together. It says, to find the gain, add the length of the stub up A to the remaining measured length of conduit after you've made your bend. Then subtract the starting length of the conduit. So they're saying that the starting length of the conduit was 48 inches, and they ended up with a 14-inch and a 36.5-inch piece. And when they add those two together, they get 50.5 inches minus the 48 inches gives them their 2.5-inch gain. Knowing the gain can help you pre-cut, ream, and pre-thread both ends of the conduit before you bend it. This will make your work go more quickly because it's easier to work with conduit while it is straight. So, figure 20 also shows the overlap developed length of a piece of conduit. The developed length, The developed length is the actual length of the conduit that will be bent. It's the amount of the pipe that you use in the bend. So developed length equals A plus B minus the gain. You can work the same example above in reverse to find the length of the conduit you started with as follows. So if you knew the gain, you could take these two and add them together and then subtract the gain, and you'd know that you had a piece that was 48 inches long when you started. 2.2.4, back-to-back 90-degree bends. A back-to-back bend consists of two 90-degree bends made on the same piece of conduit and placed back-to-back like the one shown. So here's the first bend, and then they're going to make a second bend. They're going to use that star that I told you about, not the arrow, but the star. Basically, you use this when you have to go from the back of one 90 to the back of another 90. You would measure from the back of this knockout to the back of this knockout, and it would tell you how long of a back-to-back you need. So here they're saying that they have a 12-inch stub and a 12-inch stub and a 60-inch back-to-back. So that's 24, that's 84. We've got 84 inches. And then if our gain is 2.5 inches, we would subtract 5 inches, and we should cut this piece of conduit to 79 inches, and then bend our two 90s. Using the measurements shown in figure 21, you can make a back-to-back bend by following these steps. Start by calculating the developed length, where 2 equals the number of 90. Developed length equals x plus y plus L minus the number of 90-degree bends times the gain. So we have 12 plus 12 plus 60, and that was 84 inches. And then we subtracted twice the gain, 2.5 inches times 2, which is 5 inches. So we subtracted that from our 84. We've got 79 inches. That's our developed length. Make the first bend as described earlier in the module. To make the second bend, measure the required distance between the bends from the back of the first bend. Reverse the bender on the conduit. Place the benders back to back, indicating mark at point Y on the conduit. Note that you use the outside measurements from point X to point Y. Hold the bender in the reverse position and properly align it. Apply foot pressure to complete the second bend. So, let's take a look at this. Okay, so we wanted a 12-inch stub. So we marked our conduit at 7 inches. That was 12 minus 5. And we'll take our bender and put it on our arrow facing the end we measured from. And we'll bend this up. We'll make ourselves a 12-inch stub. So here's our 12-inch stub. I know that's a lot smaller than my bender. Now we want a, I guess they said 60-inch back to back. So we're going to measure from the back of this 90. You can put a straight edge, you can put it up against a wall, whatever you need to do. We'll measure 60 inches. And we're going to put a mark on this pipe, 60 inches. I'm going to put it right there. We don't have to deduct anything. Don't deduct the take up or anything like that, or the gain, what have you. You put it right at 60 inches. Then we're going to use the star mark on this bender. We'll use the star mark, not the arrow. And you put this bender on the conduit facing the opposite end from the end you measured from. We measured from the left 60 inches and marked the conduit. We're going to put this bender on the star facing the right end of the conduit. So actually it should be oriented like this. So we'll take this guy and we'll put it on this conduit with this lined up right at that star. And then we'll use our foot pressure and we'll bend up our second 90. And when we do that, when we bend it up, something interesting is going to happen. And the end of the conduit, the edge of the conduit is going to end up, I'll use orange, and we'll see that. Let me use a color there. The conduit is going to end up, after we bend it, to be right at our mark. The mark that we said was 60 inches. When we bend this up, our conduit's going to be lined up with that 60 inches, and we will have a 60-inch back-to-back bend. That's how you bend a back-to-back. And then you just measure this 12 inches and you cut it off. What they wanted us to do is cut this conduit at 79 inches and then bend it up. And supposedly it was going to bring this up to the exact 12-inch mark. I was just bend it first and then cut it with a hacksaw. That's the easiest way. All right, let me go ahead and finish this up. I've been dragging my feet here. So that's what all of this XYZ stuff was, XYL. It's a lot better when somebody shows you. When you're in a class with an instructor and they have a bender in their hand and they show you on a piece of pipe. So hopefully you get that opportunity. I'm also going to try to make some movies. Don't know how successful I'm going to be at it, but we'll try to make a couple of videos on bending conduit. 2.3.0, and I apologize, I know this video has been going on for an hour now, and I never did take a break. I never stopped it in the middle. Maybe in editing, I might try to break it into 2 different videos. 2.3.0, making offset bends. Many situations require that conduit be bent so that it can pass over obstructions, such as beams and other conduit, or enter a rack and a junction box. This is called an offset. It changes elevation, but it doesn't change direction. It's like a jog in the road. You're driving east, and then you take this little jog in the road. But when you get finished, you're still driving due east. It's not a change in direction. It's a change in elevation. And this is the offset height. And this is the distance between bends. And that's important to know because this hypotenuse is how far apart we're going to put our two bends. And depending on the offset, the obstruction height, and the angle of bend, we'll figure out where to put that second bend. 2.3.1 offset calculations. Offsets are a trade-off between space and the effort it'll take to pull the wire. The larger the degree of bend, the harder it will be to pull the wire. The smaller the degree of bend, the easier it will be to pull the wire. Use the shallowest degree of bend that will still allow the conduit to bypass the obstruction and fit in the given space. I always like to use 30 degrees. Everybody has their preferences. To me, 30 is the best way to go because any 30-degree bend, if you're not bending a 90, bend a 30, the multiplier is 2. You can do it in your head. You need a 7-inch offset on 30 degrees. 7 times 2 is 14. Put your bends 14 inches apart. So you're making a 30-degree offset to clear a 6-inch obstruction. What will be the distance between the bends? 6 inches times 2, 12. Oh, they're doing 45 degrees. What will be the developed length, shrinkage? Make the same calculations for a 10-inch offset with 45-degree bends. Basically, the multiplier for 45 degrees is 1.414. If you have a calculator on your phone, you can always do the reciprocal of the sine of angle theta. So if you're bending a 45-degree bend, do 45 sine, it'll tell you 0.7071. Then reciprocate it, 1 over x, or x to the negative 1, and it'll give you the multiplier, 1.414. The distance between the bends equals the depth of offset times the multiplier. And here's a chart that tells us the multipliers. Actually, they're just giving us the measurements. You can figure out the calculations related to the offset by using trigonometry. Multipliers shown in Table 5 represent the cosecant of the related offset angle. Cosecant is 1 over the sine. So that's why I was saying take the sine of theta and then just reciprocate it in your calculator. You know what? I was going to say I'll show you that later, but why don't I show you that right now? Here's my calculator. Hopefully you can see it. If I'm doing a 30-degree bend and I do the sine of 30, it tells me the sine of 30 is 0.5. And then I'll reciprocate it 1 over x. And it tells me the multiplier for 30 degrees is 2. The multiplier for 45 degrees is less because it's a sharper bend. So if I have a 45-degree bend, the sine is 0.7071. When I reciprocate it, the multiplier for a 45-degree bend is 1.414. And it's nice knowing that because you can figure out other bends. You don't have to memorize them all. Let's say you wanted to make a 22.5-degree bend. All right, 22.5-degree bend to make an offset. 30 degrees was too much of an angle. You needed to be shallower to miss another obstruction overhead. Well, we'll do the sine of 22.5 and we'll reciprocate it. 2.61, that's your multiplier for 22.5 degrees. What's the multiplier for 10 degrees? 10 degrees sine 0.17. We'll reciprocate it. It's 5.76. So about 5 3/4 times the obstruction height, whatever that height is. All right. It says a magnetic torpedo level can also be used to determine the end of the second bend. Bend the conduit until the level shows that it is parallel to the first bend. So 2.3.2, making parallel offsets. There will be times when you must bend multiple pieces of conduit around a common obstruction. In this case, you'll create a parallel offset. Because the bends are laid out along a common radius, make an adjustment to ensure that the ends do not come out uneven as shown in figure 23. Here they've made 3 offsets. They're equal offsets, but look what happened. The first one fits in the box. The second one doesn't, and the third one doesn't. And if they were to put it in the box, the second one would be way down here, and the third one would be way down here. You don't want that. You want to try to keep an even distance between them. So what we're going to do is we're going to add tangent of half theta times the distance between the conduits. So whatever distance you have, if it's 3 inches between these conduits, we'll do 3 inches times the tangent of whatever the half of this angle. If this is a 30-degree bend, we'll use 15 degrees. We'll use half theta. So if it's a 30-degree bend, we'll do 15 degrees, and we'll take the tangent of 15 degrees. It's a quarter of an inch, and we'll multiply that times the 3 inches between our conduits, and we're going to increase the length of the second conduit by 8/10 of an inch. So approximately 13/16. If I don't know how many sixteenths this is, I can always just multiply times 16, and it'll tell me 12.86. It's 13/16 basically. Oops. All right. Well, I didn't mean to do that. But so this second conduit should be 13/16 of an inch longer, and this one should be 13/16 of an inch longer than the second one. There you go. Center of the first bend. Center to center spacing times tangent of half the offset angle, half of theta. So center to center spacing times tangent of half theta. They've got 12 inches, so we'll mark it at 12 inches, and then they're going to increase these two by, they're saying 12 and 13/16 and 13 and 5/8. So they added 13/16 twice. Tangents can be found using a trig tables provided, or you can use your phone. You've got a scientific calculator on your phone. So they went 3 inches between these conduits, and I don't know how much of an offset they're making. I don't know what the obstruction is, but they're using 30 degrees, so we're going to increase it by tangent of half theta. That's 15 degrees. So 15 degrees tangent, and then times the 3 inches between the obstructions. So they said it was 13/16. Well, I guess that's what we said too, 13/16. So the second bend is going to be started at 12 and 13/16, and the third one is going to be started at 12 plus 26/16, which is an inch and 5/8, so 13 and 5/8. It's double the 13/16. The equation for the amount to add can be added to the start of the first bend to find the starting point of the second pipe. That's what they did. They added that twice, 0.8037. The starting point for the second pipe is approximately 12 and 13/16. The amount added can be added to this value to find the starting point of the outermost pipe, 13 and 5/8. That's a skill that'll take practice. Making saddle bends. Saddle bends are used to go around obstructions and to bridge over obstacles such as existing conduit or plumbing running perpendicular to the intended conduit installation. So there is a 3-bend saddle. Basically, we're going to bend 3 bends. The first bend in the middle, we will bend first. And we have to add shrink to that. When we bend this first offset, this pipe is going to shrink. And amazingly enough, it's going to shrink the tangent of half theta, just like the last example we had. So if we're bending 22.5 degree bends, we can take 22.5 and divide it by 2. Oops, where did I just go? What happened here? Oh, all right. So it says figure 27 is an example of a saddle bend that clears a pipe obstruction. Making a saddle bend causes the center of the saddle to shorten by 3/16 of an inch for every inch of saddle depth. So we would multiply the saddle depth, 2-inch diameter. So we're probably going to increase this, or we'll probably make this a 3-inch 3-bend saddle, I would guess. And we'll take 3 times the multiplier or the shrink amount for 22.5 degrees. For example, if the diameter of the pipe obstruction is 2 inches, this causes a 3/8 inch shortening of the conduit on each side of the bend. When making saddle bends, use the following steps. Locate the center mark A on the conduit by using the size of the obstruction and calculate the shrink. Again, the shrink is going to be tangent a half theta. It's just coincidentally the same. I would have said a 3 inch. So 22.5 is theta. We'll divide that by 2 and get 11.25. We'll take tangent of 11.25, and that's our shrink, 0.1989. If we multiply that times 16, it'll tell us how many 16ths of an inch that is. It's 3/16 of an inch. So our shrink is 3/16 of an inch for every inch of rise. If we were going to make a 3-inch 3-bend saddle, we would multiply that times 3, and we'd get, well, 9/16 or 9.5/16. So somewhere between 9/16 and 5/8 is where we would want to, that would be our shrink. All right. So they found where they wanted the center line, and then they know how far apart to put the bends because they're using 22.5 degree. The multiplier, we said it was 2.61, and you multiply that times the height. I think they're using a 2.5 inch 3-bend saddle. Actually, we would use 2.5 rather than 2.61. We'd use 2.5. Here they're demonstrating the way that you face the bender. So the first bend is going to be done on the rim notch, the center of the bending point, for a 45 degree. Bend your 45, and then your outer 2 bends, we're going to use the arrow on the mark that we marked, and we're going to bend it at 22.5 degrees, and 22.5 and 22.5 equals 45. So that will give us our 3-bend saddle, and we'll have the center of this right on the obstruction because we added the shrink beforehand. Making 4-bend saddles. If you need to go around an obstacle that's 3 inches or larger, you might need a 4-bend saddle. It's also used, I've been told that 3-bend saddles are to go around a round obstruction and 4-bend saddles are to go around a square obstruction. So here we find this 4-bend saddle going around a 4-bend square obstruction. Step 1, determine the height of the offset. Determine the correct spacing for the first offset and mark the conduit. Bend the first offset. Mark the start point for the second offset at the trailing edge of the obstruction. Mark the spacing for the second offset and bend the second offset. So here they've marked their first offset. Actually, I can tell you a different way to do this. I always take the center of the obstruction and I add my shrink, and I find the center of my 4-bend saddle, and then I deduct half of this obstruction. I go 4 inches and 4 inches, and I make 2 marks, 4 inches and 4 inches. And when I make these bends, I'm going to be facing the obstruction, putting the hook of the bender facing the obstruction, bend this first bend, and finish this offset, and then do the same thing over here. Face the obstruction, bend this bend, and then finish the offset. But you want to do one side first. Do one side and get a perfect offset. When you're satisfied with it, don't ever touch it again. Then go on to the second one, make the second one. 2 30-degree offsets are used to form the saddle. The following steps outline how to create a 4-bend saddle. So basically, see figure 32. It says, working from left to right, calculate the start point of the first bend. The distance to the obstruction is 36 inches. The offset is 6 inches, and the 30-degree multiplier from table 3 is 2. So the distance to the obstruction minus the offset times the constant for the angle plus the shrinkage. That equals the distance to the first bend. So they're saying that 36 inches minus 12 inches, because that's 6 times 2, and then plus 1.5 inches shrink. That gave them 25.5 inches to the first mark. And then you go 12 inches to the second mark. And that's the end of the first offset. Then you would go past the obstruction and you could do the same thing laying out for the second offset on the other end. the distance to the first bend plus the distance to the second bend plus the shrinkage, that equals the total length of the first offset. Determine the start point for the second offset. The width of the box is 8 inches, therefore the start point of the second offset should be 8 inches beyond the end of the first offset. Here's the end of the first offset. We'll go 8 inches and put the beginning of the second offset. And then we'll use those same measurements, 39 inches, and we'll put the 12-inch spacing between our bends. And okay. Again, it's going to be a lot better when you've got an instructor in front of you and they can show you using a hand bender and a piece of pipe how to make these bends. I don't expect you to be able to walk into class and make a bend now that you've watched this video. This video really didn't give you the hands-on instruction that you really need in order to be able to be proficient at bending conduit. So it's not you. Don't feel bad. Don't think that you just didn't get it. You're going to need to do it in the real world before you're ever going to be able to master bending bends. And here's 2.0.0 section review. Hand benders are designed to have force applied using, and you decide the right answer. The first bend made with a hickey should be about, you decide the right answer. 90-degree bend is also known as, and making a saddle bend around a 4-inch obstruction will cause the center of the saddle to shorten by how much? Okay, all right. This concludes 26.107 hand bending, and I hope you got something out of this video. As always, if you did, give me a thumbs up and subscribe, and I'll see you on the next video. Thank you. Hey, this is Brian Young. If you liked my video, please give it a thumbs up and consider subscribing. I'll see you on the next video.